Moving on to fatty acids. We might think of saturated fatty acids as chips with regular shapes that stack closely together in a can, kind of like Pringles, right? Similarly, irregularly shaped chips that would be kind of likened to, or we can think of them as unsaturated fatty acids, they don't fit closely together. And so this actually goes importantly into how they stack. Because if they stack well like this, then they can cause clogging, right? Where if they're kind of scattered like that, it's like playing Tetris, right? If they don't stack well, then they're not going to clog. So those tend to be the ones that are better for us. All right, so what are we going to do? We're going to learn how to draw the condensed structural formula for a fatty acid and identify it, whether it's saturated or unsaturated. So fatty acids are long, unbranched carbon chains with a carboxylic acid group at one end. They're typically 12 to 18 carbon atoms long, and remember, they're insoluble in water because of that long carbon chain. They're called saturated when they do not contain a double bond between two carbons, and they're unsaturated when they do contain a double carbon bond. And so the way I think of this is, if we are saturated with all the hydrogens we could ever want, then that's going to be saturated. But the second that a double bond comes in, it actually removes two hydrogens, one from each carbon. So it's no longer saturated with all the hydrogens that could ever fit in there. So that's just a way to keep them straight in your head. So when we draw these guys, there's a couple different ways that we can think of them. So in a skeletal formula of a fatty acid, the ends and bends of the line are our carbon atoms. And the structural formula of lauric acid can be drawn in different ways. So we can draw it like this, okay, where the carboxyl group is branching off. Or you can draw it like this, where it's condensed. Or you can draw it in a nice long line structure like this. Or a lot of times they'll use the skeletal formula. What I say is, remember when we were really bored in middle school or high school, and we'd sit there and we'd be drawing letters like, oh my God, I love Johnny Depp, he's the best, right? And we'd decorate it with all these fancy bubbles. Wherever you can put a fancy bubble, that's where we can have a carbon. So practice here on the skeletal formula with me. So we would have one carbon here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Don't forget that carbon in the carboxyl group because every single carbon counts. So there would be 12 carbons, and that's how you would count the zigzags. Okay, and like I said, these guys are the same too. So with the parentheses, that just means that CH2 is repeated 10 times. So this, if we were counting how many carbons we had, we'd have, this counts for 10 carbons because there's nothing next to the carbon, but there's 2 next to the hydrogen. So this is a carbon repeated 10 times. So this would be 10 carbons or 20 hydrogens. And then there would be another carbon here and then another carbon here. So again, that would give us our 12 carbons. Same here, 10, 11, 12 carbons. So there's just different ways, and you can count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. So like I said, this guy is all the same. It's just a different way of writing things out. So when fatty acids are saturated, they only have single carbon-carbon bonds. So you can see here, there's no equal signs. And this equal sign doesn't count because he's on the carboxyl group. They're just talking about carbon-to-carbon double bonds. So you see how there's no double bonds in any of these zigzag molecules. That means that they are stack acids. Where when we are monounsaturated, remember, again, look for those root words. Mono means one. Unsaturated means that you have a double bond. So for one double bond in the whole string. So do you see here how we have an equal sign? That's our double bond. So we're going to have a double bond here, only one, so that means it's monounsaturated. Same here. There's only one double bond, and it's monounsaturated. Again, the double bond in the carboxyl group doesn't count because that is part of a different structure. We're just counting double bonds between carbon and carbon. Moving on to poly. Okay, poly means more than one. So fatty acids can be polyunsaturated, and that means at least 2 double bonds. So you see here, there's a double bond here and a double bond here. In this one, we have 1, 2, 3 double bonds. And in this guy down here, we have 4. 1, 2, 3, 4 double bonds. Okay, so just remember, look for those root words. And if we have at least 1 double bond, then that would be an unsaturated. Now, moving on to what happens to the hydrogens that are left over, okay? If we have the carbons that are on, the hydrogens that are on the same side, then that's going to be a cis unsaturated fatty acid. Where if you see here, there's one hydrogen on this side of the carbon and one hydrogen on this side of the carbon. So that means they're on opposite ends, and that means trans. Now, the way I teach this, and I start this by, I love all people except for maybe one or two in this whole wide world, okay? And if I was a boy and I dressed like a girl, society would call me trans something or other. So trans just means opposite, okay? Transatlantic flights. We're going to the opposite side of the ocean, right? So if the hydrogens are on the same side, that's going to be that cis, but if they're on opposite sides, that's going to be your trans. And kind of fun to note that almost all naturally occurring unsaturated fatty acids have one or more cis double bonds. And then I kind of think of these hydrogens as boxing, and I know that kind of sounds silly, but they're going to be fighting. Okay, so that's what causes the structure to kink, where if they don't fight for space, then they're going to be straight. So these trans-saturated fatty acids, well, they're kind of straight, and they act more like a saturated fatty acid, and so then they can like stick and cause problems on your arteries and stuff. Where when they're cis and they have that double bond, and then that means that they're going to try to stack like those zigzags that we tried to stack earlier. Okay? So then we talk about essential fatty acids. And you hear about essential fatty acids a lot in the news. Okay, they say make sure you have your fish oil and blah, blah, blah. So basically what it is it's essential that we eat them because we cannot make them. And there's a couple different kinds. Okay, there's omega-3 fatty acid and an omega-6 fatty acid. And those are our two essential fatty acids. So humans are capable of synthesizing some fatty acids from carbs and other fatty acids, but we cannot make or synthesize sufficient numbers of polyunsaturated fatty acids such as linoleic acid, linolenic acid, and arachidonic acid. And because these are polyunsaturated fats that we can't make, we have to eat them in the diet. And so these are known as essential fatty acids. Okay, it's essential that we eat them. And again, it's 3 and 6, and we'll talk about that later. Okay, so looking at the properties of those saturated fatty acids, remember that they don't have any double bonds in the fat tails, in the fatty acid tails. They're only single, and so then they can stack really well when we're playing Tetris, right? So they can fit close together in a regular pattern, and they have a strong dispersion force between the long carbon chains, and they have higher melting points that are usually solids at room temperature. And that's because they stick so close. It's kind of like cement, right? So that's good to know. All right, and then when we look at them, again, we look at how they stack. Okay, look at those potato chips, and they stack really well. They're going to tend to solidify, right? So in unsaturated fatty acids, on the other hand, or the cis double bonds are going to cause the carbons to bend or kink. Again, kind of making them act as if they didn't have a double bond when they actually do. All right, and that's going to give the molecules an irregular shape and allow for fewer interactions between molecules. So the reduced interactions in fatty acids with cis double bonds reduces the melting point of the molecule, because cis is going to be on the same side, causing it to kink. Therefore, it's going to melt easier, right? All right, let's try to apply this. So consider the condensed structural formula for oleic acid. Pause me and come back and answer these questions, okay? So what kind of molecule is an acid? Well, it contains a carboxylic acid functional group. And how many total carbons are in the oleic acid? So remember, this counts as 7, 8, 9, 10, 11 plus 7 would be 18. And that gives you 18 carbon atoms. So remember, the 7 is only because there's one carbon repeated 7 times. So that would be 7. Don't forget your carboxyl end. Okay, so is this saturated, monounsaturated, or polyunsaturated? Well, remember, it only had one double bond, so it was a monounsaturated fatty acid. And because of that, since it had at least one double bond, it's going to be liquid at room temperature, okay? And since it is long chain, that makes it insoluble in water because it was that fat, okay? So great job.